Right now, your hand is not touching anything. The desk beneath your fingers is 99.999% empty space, and the tiny fraction that isn't is just a probability wave that hasn't decided where it is yet. And that's the normal part. Because once you look at what physics actually says about reality, not what we assume, what the equations say, the simulation hypothesis stops being science fiction. It becomes the most uncomfortable explanation that actually fits the data. Number 10. The Holographic Bound. In 1972, physicist Jacob Bekenstein proved something that has never been refuted. The maximum amount of information that can exist inside any three-dimensional region of space is not determined by its volume. It is determined by its surface area. This is the Bekenstein bound, and it is not a theory, it is a hard mathematical limit written into the laws of physics. Stephen Hawking extended it through black hole thermodynamics. Juan Maldacena formalized it in 1997 as the holographic principle, one of the most studied results in theoretical physics, with over 10,000 citations in the peer-reviewed literature. Here is what it means. A sphere cannot contain more information than its surface allows. If you pack more data into a region than its surface area permits, physics itself forbids it. Not practically, not engineering-wise, mathematically forbidden. The desk you are touching is not three-dimensional matter. It is a three-dimensional projection of two-dimensional data encoded on its surface boundary. Now ask yourself, where have you seen this before? A storage medium with a hard data limit. A system where information density cannot exceed what the surface can encode. You engineer that into a system with finite computational resources. In a randomly emergent physical universe, there is no obvious reason for a maximum information density to exist at all. But in a simulation running on hardware with finite storage capacity, it is the first constraint you would impose. The universe has a hard storage limit, and we cannot explain why. Number 9. James Gates error-correcting codes. In 2015, physicist Sylvester James Gates Jr. at the University of Maryland made an announcement that rippled through the physics community. While studying supersymmetric string theory, one of the leading candidates for a theory of everything, he found something embedded in the fundamental equations of physics that had no business being there: error-correcting codes. Specifically, doubly even self-dual linear binary error-correcting block codes. The same mathematical structure used by your browser right now to detect and repair transmission errors over the internet. These codes were not inserted into the equations. They were not assumptions. They emerged spontaneously from the mathematical structure of supersymmetry, unprompted, with no reason to be there. Error-correcting codes have one function. They detect and repair corrupted data in a noisy channel. They maintain the integrity of information during transmission. They are an engineering solution to a computational problem. Finding them embedded in the equations describing the fundamental forces of the universe raises a question that Gates himself could not dismiss. He said, publicly in interviews, that he could not rule out that this is evidence we live in a simulation. In any designed computational system, error correction is one of the first features an engineer implements. A simulation without error correction accumulates data corruption. Eventually it crashes, or produces physics that is inconsistent. The laws of physics contain the mathematical signature of error correction. Their origin within fundamental equations has no accepted explanation. Nobody put them there, they were just there. Number 8. The measurement problem. The Copenhagen interpretation contains a statement that should alarm every person who hears it. Physical properties do not have definite values until measured. An electron does not have a definite position. It does not have a definite momentum. It exists as a wave function, a mathematical description of all possible states simultaneously, and it does not collapse to a single definite value until something observes it. This is not a philosophical position. This is what every quantum experiment confirms. John Wheeler, one of the most influential physicists of the 20th century, spent decades on what he called the participatory anthropic principle. His conclusion: no phenomenon is a real phenomenon until it is an observed phenomenon. He proposed the delayed choice experiment. A photon's behavior at a point in the past is determined by a measurement choice made in the future. Retroactive reality. Confirmed experimentally by Elaine Aspate's team in 2007. Now consider how an open-world video game handles rendering. It does not calculate definite states for every object in the world simultaneously. It maintains dormant probability states for regions outside the player's observation. It resolves them to definite values only when the camera demands them. Calculating everything at once would crash the system. The universe operates on precisely this principle. Reality does not exist in a definite state until something observes it. This is not an analogy. It is what quantum mechanics says, and we have never found an experiment that contradicts it. Number 7. The computational efficiency of physics. In 1942, Richard Feynman formalized the path integral formulation of quantum mechanics. Inside it is a result called the principle of least action. A particle moving from point A to point B does not take one path. It simultaneously explores every possible path through spacetime. But the paths are not random. They are weighted toward the path of least action, the most computationally efficient route given the physics constraints. Every possible path is calculated. The minimum cost path wins. This is not a metaphor. It is the mathematical foundation of quantum field theory, the most precisely tested theory in the history of science, accurate to 1 part in 10 billion. In computer science, this process has a name: optimization. Every efficient algorithm minimizes computational load by finding the least cost path through a solution space. You implement this to avoid brute forcing every calculation, because brute force is expensive and slow and will eventually exhaust your resources. The universe, at its most fundamental level, at the quantum scale where the actual mechanics of reality operate, performs exactly the optimization procedure an engineer would implement to minimize computational load. It does not brute force physics. It finds the cheapest route automatically at every point in spacetime. Simultaneously, nobody has a satisfying explanation for why nature optimizes. It just does. Number 6. The digital nature of spin. In a continuous analog universe, physical quantities should take any value on a smooth continuum. Angular momentum could be 1.5 units, or 1.50001 units, or any real number between them. In our universe, this is not what happens. Particle spin, one of the most fundamental properties of matter, comes only in integer or half-integer multiples of a fixed unit. An electron has spin 1/2. A photon has spin 1. A graviton is predicted to have spin 2. There is no particle with spin 0.7. There is no particle with spin 1.3. The allowed values are discrete steps. This extends to everything. Electric charge comes only in integer multiples of the elementary charge, never 1.5 e, never 2.7 e. Angular momentum is quantized in multiples of Planck's constant divided by 2 pi. Every fundamental property of every particle in the universe is constrained to discrete allowed values. In digital systems, information is stored in discrete states, bits that are 0 or 1, never 0.7. The difference between an analog universe and a digital universe is quantization. Our universe is quantized at every level we can probe. This is not a detail. This is the entire architecture of matter. And the architecture is digital. Number 5. The speed of light as a clock speed. The speed of light is 299,792,458 meters per second. It is not simply the speed of photons. It is the maximum rate at which any information, any causation, any physical effect can propagate through space. Gravity travels at this limit. The electromagnetic force propagates at this limit. Causality, the principle that causes precede effects, is defined by this speed. If the sun vanished right now, Earth would continue orbiting an empty point in space for 8 minutes and 20 seconds, because the causal information of the sun's absence cannot reach us any faster. In a physical universe, there is no obvious reason a maximum information speed should exist at all. Objects should interact at any speed given sufficient energy. The speed of light is not enforced by a physical mechanism. No wall, no friction, no resistance. It is written into the geometry of spacetime as a hard constraint. In a simulation, the maximum speed of information propagation is determined by the processor's clock speed. If physical interactions could propagate infinitely fast, the computational load of calculating every interaction across the entire simulation simultaneously would be infinite. The system crashes. The speed of light is a throttle, a bandwidth cap. It prevents the host processor from being overwhelmed by calculating instantaneous interactions across infinite distances simultaneously. It is not derived from more fundamental principles. No deeper law produces it. It was set, and everything in the universe obeys it without exception. Number 4. The simulation argument mathematics. In 2003, Oxford philosopher Nick Bostrom published a paper presenting a formal logical trilemma. One of 3 statements must be true. Statement 1. Virtually all civilizations at our level of development go extinct before reaching the computational capability to run realistic simulations. Statement 2. Virtually all post-human civilizations that reach simulation capability choose not to run simulations of their evolutionary history. Statement 3. We are almost certainly living in a computer simulation right now. The argument is mathematical, not philosophical. If Statement 1 and Statement 2 are both false, if civilizations survive and choose to simulate, then the number of simulated realities vastly outnumbers base realities. A single post-human civilization running 10,000 ancestor simulations creates 10,000 minds for every one mind in base reality. If you select a random conscious mind from all minds in all realities, the probability of selecting a mind in base reality approaches zero as the number of simulations grows. The argument has been endorsed as serious by Stephen Hawking, Neil deGrasse Tyson, and Elon Musk. It has been cited in peer-reviewed physics journals. It does not prove we live in a simulation. It proves that the only way to make the probability significant is to argue that either civilizations always go extinct before simulating, or they always choose not to. Both positions require explaining a universal pattern of extinction or restraint across every advanced civilization in the universe. No such explanation exists. Number 3. Max Tegmark's mathematical universe. MIT cosmologist Max Tegmark has published a formal scientific hypothesis in peer-reviewed journals including Foundations of Physics. His argument, the universe is not described by mathematics. The universe is mathematics. Every physical property of every object reduces to mathematical relationships. There is no additional substrate beneath the equations, no underlying physical stuff. The equations are not a description of reality. They are the reality. Eugene Wigner identified the problem in 1960. He called it the unreasonable effectiveness of mathematics. Abstract mathematics developed with no reference to physics repeatedly turns out to be the exact language of physical law. Complex numbers, invented to solve polynomial equations, perfectly describe quantum mechanics. Differential geometry, pure mathematics, turned out to be the structure of general relativity. Group theory from abstract algebra turned out to be the standard model of particle physics. Why does the universe speak mathematics? Not approximately, precisely, not usefully, perfectly. Tegmark's answer, a universe made entirely of mathematics is indistinguishable from a universe made entirely of code. The atoms in your body are not made of stuff. They are made of mathematical relationships, information executing according to rules. If that is true, the distinction between reality and simulation is not a question of truth. It is a question of perspective. Number 2, the fine structure constant. The fine structure constant is approximately 137th. It governs the interaction between light and matter. It appears throughout quantum mechanics and electromagnetism. It is dimensionless, no units, and it is not derived from any more fundamental theory. It is measured and found to be what it is. Richard Feynman called it one of the greatest mysteries in physics, a magic number that comes to us with no understanding by man. If the fine structure constant were 100th, chemistry would be impossible. Electrons would be too strongly bound for chemical reactions. If it were 1/150th, matter would be too weakly bound for complex structures. The range of values permitting chemistry, stars, and life is extremely narrow. The fine structure constant sits within that range without explanation. It is not alone. The universe contains 26 fundamental constants, all dimensionless, all measured rather than derived, all sitting at values that permit physics, chemistry, and observers to exist. In any designed simulation, the programmer sets the fundamental constants by inputting specific values into the physics engine. These values are parameters, chosen numbers, not derived results. They do not emerge from deeper physics. You input them. The 26 constants of our universe behave exactly as parameters behave. They are specific, they are not derived. They are precisely calibrated to produce a stable, complex, observer-generating environment. We have no other explanation for why they have the values they do. Number 1, the conscientious observer problem. The universe brought observers into existence, and then required them. The double-slit experiment demonstrates that physical reality at the quantum level does not collapse to definite states without observation. The wave function, the mathematical description of all possible states, remains unresolved, suspended in superposition, until an observer interacts with the system. John Wheeler proposed, and never retracted, the participatory anthropic principle. the universe required observers to bring itself into existence. This is circular. It is also consistent with every quantum experiment ever performed. The strong anthropic principle states that the universe must have properties compatible with the existence of observers, because we observe it. When combined with the fine-tuning of 26 constants, it implies those constants were tuned specifically to produce observers. The universe was not tuned to produce rocks, not tuned to produce energy, tuned to produce conscious observers, capable of measurement, observers whose active measurement is required by the laws of physics to collapse quantum reality into definite existence. In a simulation, the purpose of the system determines its design. A simulation run to generate conscious observers would be designed with exactly the physics we see: fine-tuned constants, quantized matter, observer-dependent wave function collapse, a maximum information speed, computational optimization. And the observers it generates, after 100 years of quantum mechanics, arrive at exactly this question. Do we live in a simulation? The universe was configured to produce minds capable of asking that question. And the answer, after everything we have measured, is that without observers, reality at the fundamental level does not fully exist. Think about that. 10 pieces of evidence. One pattern. The universe has a storage limit. Its equations contain error correction. Its properties are discrete, not continuous. Its maximum speed behaves like a clock rate. Its particles only exist when observed. Its constants are set rather than derived. And its mathematics is not a description of reality. It may simply be reality. None of these facts individually proves anything. But they do not point in different directions. They point at the same thing. A universe that behaves, at every level, like a system designed by something that needed it to run. Whether that is terrifying or liberating probably depends on whether you think the programmer is still watching. If you want to see more videos like this, click the video on screen now.